Hello, and welcome to the Trepa Technologies Security Plus course. My name is Johnny Bandon, and I will be your instructor for this video series. This video will cover Domain 2.8 Cryptography Concepts. Now let's get started. Cryptography is a very challenging concept for new students to wrap their heads around. In security, cryptography is actually an old concept that has been used for ages, even back to like the Roman era. Even back in World War II, we used cryptography to protect transmissions. Learning the fundamental cryptography concepts is an essential part of learning how to actually secure your data and use cryptography to secure your data. The key to learning and understanding cryptography is the same as learning a new language. We must understand the language of cryptography, and then we can learn how cryptography is implemented and used in our enterprises. So we must understand this vocabulary, right, and what it means, and then we can get into actually doing the implementations, right? So this section or this slide deck is going to go over cryptography concepts. And then if you want to see how we can employ these concepts, look for our bonus videos in our Security Plus playlist. So keys in cryptography are the binary value that we use in our cryptography algorithms that determine the size and strength of your encryption algorithm. So we have algorithms that encrypt our data. The larger the key, or the bigger the bit size of the key, stronger the algorithm, right? Crypto keys are the key, right, to protecting your data. For example, if we want to use the triple DES encryption algorithm, we will need a key to execute the triple DES algorithm. So if we want to use triple DES to encrypt our data, we need a key size. There are many different sizes we can use. We have 56-bit key, 128-bit key, or 192-bit key, right? The larger the key, the more robust the encryption is because of how many times it's going to be encrypted by that larger key, right? So that's the importance of these keys. A crypto key is different in bit size. Now let's go over ciphers. So ciphers are the algorithms used to perform encryption on data. And there are two different ciphers we can use to encrypt data. A block cipher will encrypt chunks or blocks of data at one time, right? A stream cipher will encrypt data bit by bit instead of in chunks. Stream algorithms are faster and more efficient than block ciphers because they encrypt only one bit of data at a time rather than entire chunks or blocks. Block ciphers are used to encrypt data at rest since there's much more to encrypt when we're talking about the storage on our networks, right? So if you want to encrypt data at rest, do full disk encryption on terabytes of information, you're probably going to want to do a block cipher, right? And then stream ciphers are typically used to encrypt data in transit since it encrypts per bit. So when you use TLS technologies, that cipher suite that you use is usually going to use different stream ciphers for that data in transit. And in cryptography, there are two different types of algorithms and encryption types we use: symmetric and asymmetric encryption algorithms. In symmetric algorithms, a cryptography key is used to encrypt plain text, which then turns into ciphertext. That same key will then be used to decrypt that data back into plain text to be readable and processed by a system or user. Because the cryptography key is the key to encrypting and decrypting, the sender and receiver must know the same key, right? Because of this, the cryptography key must be protected. In symmetric encryption, only one private key, right? That's what we call it, a private key, or we can call it a secret key, is used for encryption and decryption. And both the sender and receiver must have this private key. So how do we securely transmit the private key between sender and receiver, right? Because the whole purpose of encrypting data is that no one can look at it. We have confidentiality, right? That's the main point of all this, is that we have confidentiality of our data. Well, we if we're using symmetric key algorithms, we're going to have to send our private key out of band, right? Out of band. Which means we must use a secure key exchange to ensure a malicious actor cannot steal our private key and then be able to decrypt our confidential data. Because of the singular key use in symmetric encryption, meaning if I want to encrypt and decrypt, I have to use one key, it doesn't scale well in large enterprises that always need to encrypt data in transit between multiple senders and receivers, right? I don't have it up on the slide, but there's a formula that says if you have 20 users using symmetric algorithm, there's going to be a crazy number of private keys that have to be used, right? So the solution for this shortcoming in symmetric algorithm is using asymmetric key encryption algorithms, which we're going to talk about in the next slide. So asymmetric key algorithms use public and private keys for encryption and decryption. For example, let's take a look at this screen here. Let's say our sender, Amanda, wants to send encrypted data to Dave. Amanda will encrypt her data in these steps. First, Amanda will take Dave's public key, right? So she's going to grab Dave's public key, or excuse me, she's going to take Dave's public key and use it to encrypt her data. Once Amanda has encrypted using Dave's public key, she will transmit the data, which is now in ciphertext, right? Once that data reaches Dave, Dave will then use his private key to decrypt that information, turning it back into plain text. We call this using a public-private key pair. Dave's private key is the only thing that can decrypt information that has been encrypted using his public key. Because we use public keys in asymmetric encryption that can be published out to every user in our enterprise, maybe using something like a public key infrastructure, right? This fixes that scalability issue with symmetric encryption, right? So again, to kind of go through the flow again, in asymmetric key algorithms, our sender is going to use our receiver's public key to encrypt, and then the receiver is going to use his or her own private key to decrypt. And now let's go over hashing, another important part of our cryptography concepts. So hashing is a mathematical computation performed on data to create a hashed text or message digest, which is a unique string of characters created from the file or data you are hashing. When this file changes, the message digest will also change. And you'll have to rerun a hashing algorithm against that changed data. We can use hashing to verify the integrity of our data. For example, let's say you install a program online. Like let's say you install Notepad++. Typically, a vendor will provide a list of checksums or digests created when they created that program. Meaning when you go to install that or download that exe online, they'll also say, hey, also download our list of checksums, which have different checksums for like SHA, MD5, all different hashing algorithms, right? So you download that list of digests / checksums, and then when you actually run the hashing algorithm against the program executable or the install file, you can then compare the checksum you computed to that list of checksums and digests and ensure they are the same to verify that the installation package has not been changed in transit. Now, if this doesn't really make sense right now, right, because you're not seeing it, again, check out our bonus videos where I'll show you how to get a message digest using command prompt on a Windows machine and then comparing it to that list of digests from online. And then we have salting. So we can add additional protections to hashing by using a technique called salting. Salting adds additional text / data to the original file / data to create a unique hash that will not be vulnerable to a hashed file that doesn't have that additional text. So what do I mean by this? Essentially what we're saying is that salting helps prevent against a rainbow table attack, which is a list of pre-computed hashes that attackers can use to brute force a hash, right? So this also prevents something called collisions. What collisions are is you getting the same hash from data that isn't the same, right? So if we add this salt, we change our data just a little bit so we always get those unique hashes. And this will also eliminate the possibility of collisions or a rainbow table attack. And now let's go into our different hash functions. So SHA, which is the secure hash algorithm, is one of the hash functions that is the most secure for hashing technologies. The latest implementation of SHA is SHA-3, and SHA is actually recognized by NIST, right? By the National Institute of Standards Technologies as the most secure. And just like everything in encryption, the higher the bit size or the stronger the hash. So to get the most secure hash, we want to use SHA-512, right? Then we have MD5. This is another hashing algorithm that is no longer secure because it is prone to collisions. And again, collisions are when two digests are the same but are created from two different files. So this doesn't ensure the integrity of your data when a hashing algorithm is prone to collisions. Another cryptography concept we have to talk about is digital signatures. Digital signatures work much like in asymmetric encryption by employing a public-private key pair to ensure integrity and also non-repudiation for our data in transit. So how does this work? A digital signature works because the signer/sender will run a hashing algorithm against the data it's sending, and then it will encrypt that hash, the actual hash digest, using the sender's private key. Okay, so a little bit different. We're going to use the sender's private key to encrypt that hash, and then once that hash is encrypted, you will actually have that digital signature. You will then attach that digital signature to the data you are sending. So you attach that digital signature maybe to that email you're sending. Then, once the receiver receives your message or your data, the first thing it's going to do, the receiver that is, it will decrypt the signature, right, using that public key. And then it's going to perform the same hashing algorithm against the data and then compare the two hash digests, right? And if they're the same, then you've just ensured non repudiation and integrity of the data. So let's break this down, right? So let's say you want to send an email, right? This guy is Bob. This is Alice. Bob wants to send an email. Well, he wants to attach a digital signature. So how does that work? So the first thing that's going to happen is you're going to run a hashing algorithm against that data, and you're going to create a unique digest. And then using that public-private key pair, you're going to encrypt that digest using the sender's private key, okay? And then once you encrypt that digest, you've now created your digital signature, and you're going to attach that digital signature to your data or your email. And then once the receiver Alice gets that email, the first thing it's going to do is decrypt that encrypted hash, right? Run that same hashing algorithm, and then compare the two digests, right? And if they are the same, then we know that nothing's been changed in transit. And now we can verify the integrity and also the non-repudiation. All right, so we have talked extensively about how your private key must be protected from threat actors. But how do we ensure the senders and receivers both know the private key, right? We talked about this a little earlier. We must use a key exchange algorithm. And asymmetric key algorithms, they obviously do not require a key exchange algorithm because they're going to use this public-private key pairs for encryption. But in symmetric encryption, keys will need a key exchange algorithm to exchange the private keys between sender and receiver. So Diffie-Hellman is a key exchange algorithm we can use to transmit private keys. Now, the ins and outs of our how Diffie-Hellman works, they're not required by the Security Plus exam. The only thing you need to know really is that Diffie-Hellman is a secure key exchange algorithm used for symmetric encryption. And then we have ECC, which stands for elliptic curve cryptography. This is another key exchange algorithm we can use to send private keys securely. And this uses the curves on a line graph, right? And again, we're not going to get deep into this. We're not getting our doctorate in cryptography, right? But just for the Security Plus exam, you must know that it's a key exchange algorithm. All right, I want to thank you for viewing this video, and stay tuned for our next video where we'll be going into domain 3.0. And that first video we'll be going over is domain 3.1 secure protocols. And again, a lot of this cryptography it's hard to learn first time around, right? So please use other resources to learn. Professor Messer is a great resource. Go look at the security exam book and check out our bonus videos. Well, I'll show you some like how to hash and how we can use encryption, right? How we do encryption on bulk storage, stuff like that. So I want to thank you for viewing. And again, stay tuned for our next video where we jump into domain 3.